Hello and welcome to this lesson on accuracy, precision and error. In this lesson we'll try and develop an understanding of accuracy and precision as well as the different types of error. And we'll apply those ideas to some of the practicals that you will have done during Year 12 Physics. So all good scientific theories depend on good scientific measurements. And any measurement taken within science, in order to be a good scientific measurement, must be valid, repeatable and reproducible. Let me explain what each of those terms mean. So a valid measurement is a measurement that is taken using a proper method, and indeed it is one where the measurement is being taken on the right thing that actually needs measuring. Reproducible measurements or reproducible results are obtained using a method that the original experimenter could use a second time and get the same results and the same conclusion. Reproducible data does not necessarily mean that the same experiment would be performed, but rather if a different group of people performed a different experiment, they would still arrive at the same conclusion despite using different equipment or techniques. So errors are part and parcel of every measurement that is taken within a scientific experiment. Errors are not necessarily a reflection of the poor design of an experiment or the lack of ability of an experimenter. Rather, they are down to three causes, and good experimental methods will seek ways to mitigate each of these. So the first source of error is caused by the precision of the instrument being used to make the measurement. This is known as the uncertainty, and in the next lesson we will deal further with this topic. But essentially it can be dealt with by an appropriate and correct choice of instrument. The second source of error is known as systematic error. This source of error can come from poor use of equipment or an unaccounted aspect of the experimental design. The third source of error is random error. This source of error is present in virtually all experiments. We see this when there are differences in readings and yet no obvious pattern or bias in the differences. A typical way to reduce the influence of random error is by repeating an experiment and discarding outliers and therefore calculating a mean. One thing to mention here, there is no such thing as human error, and so human error shouldn't ever be referred to as a source of errors. Rather, we always refer to one of these three sources of error. I'd now like to cover these three terms: accurate, reliable and precise. These are three terms which are often poorly understood and easily confused. In this section of the lesson I hope to explain these to you using a target practice analogy. Let's start with accurate. An accurate shooter would be able to fire several rounds at the target where the average position of the shots is in the center spot. Well, you might be tempted to suggest that the diagram here isn't particularly accurate as there are many wide of the mark. Yet overall, the average will be in the center, and this is what is determined as accurate. Here is where accuracy and the other terms can then easily become confused. What we say here is that an accurate result is one where the mean result is equal to or close to the true value. Now let's look at reliable. In this example, you can see that each of the shots is in a very similar position on the target, and yet they're not very accurate because all of them are away from the center point. Reliability or reliable results are where there's a very small spread in the data, so most of the data points are very close together. This is reliable. The final example is about precision. The shots on the left of the target are more precise than the shots on the right of the target. Those on the right cover a very large area as they're large shots, whereas those on the left cover a very small area. There's a precise area that the shots on the left cover. When thinking about scientific data, precise measurements cover a very small range, whereas imprecise data has a large range for an individual reading, or we could say a large resolution for individual readings. So here is the data from 3 experiments used to measure the frequency of a wave. Each experiment used a different method and different equipment, but the same wave was being measured, which is a frequency of 438 Hz. What I'd like you to do is I'd like you to rank each of these in order of accuracy, reliability, or precision. I'll do the first one for you, which is accuracy. So to determine accuracy, we need to calculate the average. Group A's average is 440 Hz, and I'm giving my answer to the same resolution as the data in the table. Group B's average is 438.0 Hz, again to the same resolution as the data in the table, and Group C's average is 440 Hz. Though I calculate Group C's average to be 436.67 Hz, I need to give that as 440 Hz because that's the resolution that we've got there in the table. So therefore the most accurate group is Group B, followed by Group A and C in joint last place. So what I'd like you to do is pause the video now, and then you can determine the rank of the reliability and the precision of these 3 sets of data. Unpause the video when you're ready. So hopefully you have ranked these data in the following way. Group A data is the most reliable because it has the smallest range of values. The largest is 441, the smallest is 439, which has a range of just 2. Group B is next best with a range of 4.4, and Group C has a range of 10. Lastly, precision. Group B here has the most precise data, as this is given to 1 decimal place, a resolution of 1 decimal place, whereas Group C is the least precise, as it appears they are using measuring instruments that were only able to go to the nearest 10 Hz. So for the 8 situations below, I'd like you to consider whether these effects would make them more or less accurate, reliable, precise, or whether they'd introduce random or systematic errors or larger uncertainties. At any time you can now rewind the video to review the definitions and the explanations of any of those key terms. Let me consider the first one for you to show how we can go about doing this. So in the first one, we're measuring a mass of a piece of string for the standing waves practical, and the digital balance has been placed underneath a constant draft that might be present in the laboratory. Hopefully this will be fairly obvious in terms of its effect. It's going to affect the digital balance by placing a downward force on the digital balance, causing it to read larger values than the true value. So this will be a systematic error. It's going to affect all of the results, and it's going to cause those results to be less accurate. Nevertheless, the precision of the results will be unaffected. The digital balance will still read the same number of decimal places, and assuming the draft is constant, then the reliability of the results would not be affected either, because the same amount of draft will be present on all of the readings. Hopefully you can see that this is a really easy one to mitigate against, either by ensuring the digital balance always reads 0 prior to adding the masses, or by moving the balance to a less drafty part of the laboratory. So I'd like you to take a similar approach to the remaining 7 problems. Pause the video and then unpause when you have finished, and then the rest of the video will show the suggested answers to these questions.